All right, today we are going to be talking about scatter plots. There is an optional note sheet that you can choose to print off or ask your teacher to print off for you if you would rather have that in front of you. We are going to go through some vocabulary words, so make sure that you have these written down somewhere in your notes or on your vocabulary sheet. The first one is an arithmetic sequence. Now, some of your teachers might call it an arithmetic sequence, some of them might call it an arithmetic sequence. Okay, so either way is correct. And that is when you are adding or subtracting by a constant number with a group of numbers. Okay, so adding or subtracting, so hopefully you remember that that means linear. Okay, so arithmetic is a linear sequence when we're adding or subtracting by that same number. So notice in this sequence we go from 5 to 8 to 11 to 14 to 17. We're adding 3 every single time. Okay, we could also do a sequence like this, okay, where we are subtracting by 2 every single time. Okay, a sequence that does not work would be going from 1 to 2 to 4 to 7 to 11. Notice we are adding 1, then adding 2, then adding 3, then adding 4. It has to be a constant number. Okay, it can't be different. Okay, so this does not work. Okay, so take a minute and write this down. Write down an example. Next, the majority of this lesson is going to be dealing with scatter plots. Scatter plots is a coordinate graph with coordinate points scattered all over the data. I think most of us have dealt with scatter plots before, okay, but this is an example of one. You don't have to write it exactly as shown, okay, but you can do a quick sketch, okay, and just put some dots like that to show that it is a scatter plot. Next is a line of best fit. So for scatter plots, if you notice that the data can sometimes be random, so it's important that scatter plots, we will be drawing in a line that best fits the data. Okay, so looking over here at this example, notice this red line or this red graph that we drew in. It goes through a few points, not exactly through, but it's around most of the data. Okay, it's a line that goes in the direction of the data, and it's the average of the data. Okay, so I wouldn't want to put my line of best fit going this way because that's not where my data is going. Okay, when we do draw lines of best fit, okay, sometimes we might be a little off from somebody else, so maybe your line of best fit would look like this, or maybe look like this, okay, but as long as it's going in that same direction, and it's about the average of the data. Okay, so you can sketch an example like the one shown. Okay, if you want to put a couple examples, notice this one, I had my dots kind of trending upwards. So my line of best fit would be probably somewhere through here. Notice that about half the data points are above the line, about half are below the line. There isn't an exact science behind line of best fit. Just make sure you're getting somewhat close to the data points. Last vocabulary word would be correlation. Correlation is the direction or trend of the data. So looking at this first picture, we notice that the data is trending upwards, right? Okay, it's going upwards, so we would call this a positive correlation. Because the data, if I'm looking from going from left to right, okay, it's going upwards. And this one, as as I look at it left to right, it's going downwards. So that would be a negative correlation. Then looking at the last one, sometimes our scatter plots are just going to be random. There's not going to be a direction. Notice these points are kind of all over the board. Okay, we can't tell if it's going upwards or downwards or which way it's going. Okay, there's no exact trend. So this one would have no correlation. So I want you to sketch all three examples in your notes. All right, we are going to be dealing with this scatter plot for the next few slides. And I'm just going to go through and talk to you about some problems that might show up when we are dealing with scatter plots. Okay, so I want you to take a look at the graph. Okay, notice that we're talking about bridge length and we're talking about the painting cost. So this would be like going and painting a bridge. Okay, so if they were 100 feet long, it'd be about $20,000 to paint it. Okay, and then if it was about 500 feet long, it would be about $80,000. Okay, so that's just kind of what the graph is showing. So first, how do you think the cost estimators decided on where to draw the line? Okay, so this line obviously doesn't really go through any of the data points, pretty close, but I want you to think about why you think they drew the line there. Okay, they probably didn't draw the line anywhere else, because if they were to draw their line up here, okay, or down here, it doesn't go through the data. Okay, they wanted to best represent the data or get the best average so that when companies came to them, that they could give them the best estimate for the cost. Okay, so they used the line of best fit. Okay, they wanted to try to get through as many points as they could so that they could give a good estimate. Next, what does the info from the line of best fit give us that the points alone do not? So if you look on the graph, there are only 4 points that they gave us. Okay, and my first thing that I think about is, well, what if we have a bridge that's 150 feet long? Okay, so if I look at 150 down here, there is no point. Okay, or if it was 250 feet long or 350, right? There's no point that goes to them. So the line of best fit helps us find those like in-between points. They help us find all of the different lengths for the bridges. Okay, so it gives us that more information like I was talking about in the last slide. What information do you need in order to write an equation for this line? Okay, so we're in the linear unit, so we're going to be using y equals mx plus b. So what information would I need in order to complete this? It's not a trick question. I would need the slope, and I would need the y-intercept. Okay, so let's figure those out. First things first is, what would be the y-intercept of this graph if we're looking at the line of best fit? Now, this isn't going to be exact, okay, but we can use our best guess based on the line and the information given. Okay, so the y-intercept would be right down here. Okay, and notice that we are going up by tens of thousands for every mark here. Okay, so I would say it would be around 5,000 for our y-intercept. Next, how would we find the slope? So I'm going to find 2 points on the line. So notice these points are not exactly on the line. Okay, so I'm going to use this point up here is on a nice intersection, and this point over here is on a nice intersection. Okay, and then I want to find the rise over the run. Now, if you remember when we did rise over run, on a graph we had to pay attention to the scale factor. Okay, so I already said it in the last slide that the y's is going up by 10,000 every time. So we're not just going up by 1, 2, 3. We're going up by 10,000, or 10,000, 20,000, 30,000. And then across the bottom, what are we going up by every time? Okay, where every space represents 50. So 50, 100, 150, 200. So my rise over my run. And if you simplify this, if you take 30,000 divided by 200 in your calculator, okay, you should come up with 150 for your slope. So if we are writing an equation for this graph, we would write, we got 150 for our slope, and we said about 5,000 for our y-intercept. So now the contractors, okay, or the painters, can use this equation for any length of the bridge that anybody comes to them with. So they could go to a 600-foot bridge, and they could plug 600 in to figure out the estimated cost. All right, let's do some estimating based on our line of best fit. So it says, use the line of the equation to estimate the painting costs for bridges that are similar bridges that are 150 feet or 280 feet. So first, 175 feet. That would be about here. So if we go up and over, it looks like we'd be at about $30,000. Okay, pause the video and try to come up with the answer for 280. Pause it. Okay, at about 280, okay, we'd be right in here. Okay, so I would say it'd have to be under 50,000. So maybe like 48, 47, somewhere around there, seem right? Okay, so somewhere around there. Obviously, it's an estimate because we don't have a big enough graph with exact numbers on it. Next, okay, now they want to estimate the length if we're given the amount. So then we'd use our y-axis to go to 10,000. So remember 10,000 would be right here. We'd go over and down. So it would be somewhere between 30 and 40 feet. Now again, it's an estimate, okay? So it might not be exactly like mine. Then if we go up to 60,000, well, that wasn't really that close, but I would say around 360 to 375-ish feet.